Good afternoon to all of you. Good afternoon, Devesh. Let's go ahead with today's lecture. Today's class, we are going to talk more on what we had started in the last class. We started last class talking about the acoustics parameters of small rooms, small studios, etc. So, we are going to talk more on those lines today. Yes, good afternoon, Namishka. This is the 30th lecture which I'm taking. We were talking about sound images. We continue to talk a little bit more on the sound images. Then we will speak about multi-channel sound recording and maybe a little bit about reproduction. We are going to talk about diffusers and absorbers, the role they play in a acoustic environment, and we are going to take up some problems. With that, we end this chapter. As I said, the chapters now are going to be small, they will end quickly. I request you all to get your pen and paper handy so that if some, and of course calculators too, so that if some problem solving is needed, you can do it quickly. So going ahead, first of all, sound images. In the last class, we spoke about that if there are more than one sound sources present, then the resultant source of sound can be either one of them, or it could be altogether a third source, which is called a sound image. So we have already seen an experiment for images. The person sits here at the center, left, right. On this, we plot how much is the delay from the left speakers. Delay from the left speakers means how more far away the left speaker is from the person. So what we do practically, I mean what we try to understand is, if I shift L behind and if I drive both the speakers by the same signal and shift L little bit far compared to right speaker, then a delay is introduced in the left speaker. Other way to introduce the delay or mimic the same effect of shifting the left speaker physically behind is to feed the same signal to the left speaker little later. So that delay is plotted over here, and the compensation, the delay has been compensated by making L louder. So if L is louder, like let's take the first an ideal case when left and right speakers are at the same intensity and at the same distance, the combined source appears to be at the center. That is the image of the sound source. Resultant image is at the center. You will perceive that the sound is neither coming from left nor coming from right. It will come from the center from a single source, provided if both the sources are equidistant, that is, there is no delay in the signal coming from any one of the sources, and both the sources have the same loudness. If you push L behind, that is, if you introduce a delay from this delay in the signal from L, then in that case you can make L little louder compared to right side, so that the image will appear again at the center. So here are all those possible values. This line gives you all those possible values for which the delay can be compensated by increase in the volume level. So this is difference in the decibel level. As you can see, as the delay increases, the you have to compensate by increasing the volume further. The only issue is that it does not follow the curve beyond this point. Beyond this point, your loudness level will not impact that, will not uh, compensate the delay. So we have seen this experiment in the last class. Now, what will happen if the phase is reversed? That is, if, if the two sources equidistant, same loudness, but they are fed with different phases, then what happens is the signal, as I said, if the equidistant, same loudness, the resultant image is at the center in the front. But if the phase is reversed, then the resultant image jumps from front to back. So it appears that the source of sound is kept behind. I mean, these are the parameters which can be altered, tweaked in order to make a sound moving, or to give the feeling of a moving sound in a room. Reduced strength of the signal will make the image move beyond the other speaker. So, for example, I have two examples over here. The front to back is the first one. The source feeds left speaker and right speaker, but they are fed phase reversed. You can see from the source, this is uh, crest and trough, and this is trough and crest. So if they are fed with identical signals, the resultant image is in front in the center. But if they are phase reversed, the resultant image is behind. Now, what happens here is, if one of the signal is made weaker in the strength, signal strength, then the automatically the signal, sorry, the resultant image shifts to the louder speaker. So if left is made weaker, the image will shift towards the right side speaker. So all these parameters can be used dynamically, controlled by a software to produce the impact of a moving sound in a room. Apart from this, the other parameter is the size of the image. Remember, the speaker, more or less in a large hall, can be considered as a point source of light. I'm sorry, point source of sound. So your image is also a point image. Now, if you have two sources, then the image is point image. Resultant image is also a point image, but sometimes the size of the image can also be altered depending upon the crossover between the two sources. So I would request you to read more on this from the references. So the important point that we have to remember, that there is the degree to which the fusion of multiple images into a single image happens. The fused image can be broadened, can be narrowed by controlling the crossover between the two sources, and the displacement of image in the space. So how the sound source moves from left to right. Many people might not experience this in a normal music system, but in many headphones, these effects can be manipulated. So music moves from left side to right side, and in auditoriums, definitely, if the car is moving in an auditorium, then the impact comes in the form of sound moving from right to left. We will talk more on those aspects in a while. The factors that affect are, we have already discussed, the difference in the sound level, spectrum, phase, time of arrival, and reverberation sound between the two sources. Now, this is a very common word, high fidelity sound or hi-fi sound. If you if you look at the advertisement of musical systems, I mean, we are living in a world where everybody has a mobile phone and you can listen to music and all. But not long ago, maybe 10 years back, 15 years back, the world was a very different place. If you had to listen to a music, most of the time, what you had at hand was a dedicated speaker music player system. So, and those days these words were very common: hi-fi system or high fidelity sound, etc. So technically we define high fidelity sound, which has following characteristics. The sound spectrum of the reproduced sound should be identical to that of the source. That's very obvious. Your source produces certain frequencies, but your reproducing system can't produce those frequencies. Then the fidelity we say is poor. So that's a very obvious thing. For example, if the source has a very low frequency musical instrument like an Indian musical instrument called dholak has a very low frequency, especially on the heavier side. Most of the music systems which are commercially available in the market, you will find that will not be able to produce or reproduce that sound. So if you want those sounds to be reproduced, then this reproduction system should have identical spectrum or frequency response to that of the source. The reproduced sound should be free of distortion and noise. So we have already spoken about the various kind of distortions and some type of noises. More on the noise will come in the next chapter. So the reproduction should be free from distortion and noise. The reproduced sound should have loudness and dynamic range compared to the original sound. That's correct. Original sound might be very have a large dynamic range. Typically, if you hear music performance live, you will hear the instruments ranging from very low frequency end to a very high frequency end, and very low volume loudness to a very high loudness. So all these should be reproduced by the reproducing system. So that's another requirement. And the spatial sound pattern of the original sound should be reproduced. So, for example, a music arranger arranges a music in a way that live audience gets, say, all high frequency instruments like a guitar on the left side, while all low frequency instruments like a drum on the right side. So, if that is the arrangement of the music arranger, what will be the arrangement, I mean how the reproducing system is reproducing the sound. So if you're listening to the sound, then is that separation really happening? The left hand side and right hand side systems, are they giving different impacts? So that is another parameter that has to be taken care. And of course, reverberation characteristics. The live sound has some sort of reverberation or reverberant effect in an auditorium, etc. So it should be preserved and it should be reproduced faithfully. The live listening environment has the impact of reverberation, which has to come in the later on recorded listening environment too. Now there are multi-channel sound reproducing systems. I will take them quickly. This is a first or simplest kind of recording system. It is called a monophonic recording system. Here what is happening is this one microphone which records the sound. There is an amplifier. Amplifier will have a preamplifier and an amplifier, as we have already discussed somewhere else, and then a loudspeaker. So this is single channel recording. You have one channel and one amplifier and one speaker. This is typically referred as a monophonic recording. Monophonic recording has some variations. So here the monophonic recording is happening, but it is produced to one ear only, not to both the ears. So this is a monophonic but also monaural. This is biaural. So this is the third way. This is also monophonic in a sense that you have a dummy head and the recording mics are placed as if there are two ears of the dummy head. So this will record the sound from this side, this will record the sound from this side, but essentially they are very close to each other and they act like a single recording device that is amplified and fed to the two speakers, left and right speakers. This is a monophonic recording once again, but this is binaural presentation. So you are presented to both the ears separately. A true stereophonic recording goes this way, where the two microphones are kept at some different distances or at some different angles to each other. They are amplified, and the reproduction is again by different speakers, so left and right. And this is a true stereophonic recording. There are a number of possible combinations. You can place the two microphones in number of ways, and you can put the two speakers left and right also in number of ways. And then there are multi-channel recording which produce normally a true, what is called a true surround sound. So you have a number of microphones and these numbers can vary. Can you guess how many? It could be 4 channel, it could be 8 channel. The maximum I have heard is a 32 channel recording. So there are 32 microphones placed in the recording environment at different positions and different angles. The signal processing system processes the signal and reproduced by as many number of speakers as well. So this is a multi-channel recording here. So there are many ways by which the sound can be recorded. Present day, it's mostly multi-channel in all commercial work. Stereophonic sound is typically very common. Most of the mobile phones also these days can record stereophonic sound. Two microphones, two speakers are required. As I said, there are a number of possible combinations. One of the most popular possible combination is Bloomline pair or pair of bidirectional microphones. So two microphones which are in two different directions. Typically they are kept at 90 degree to each other. One microphone typically has a pickup pattern of this side, this type, which is of 8 pattern. The distance from the center gives the strength of pickup. So it has a very high strength of pickup in this direction, medium strength of pickup in this direction, but very less strength of pickup in this direction. So this is single microscope's pickup pattern. You can combine two microphones at 90 degrees, so left and right. So their pickup patterns also overlap in such a way that they tend to cover the all 360-degree region in a perfect manner. So this is the one of the ways the two microphones are placed. You will find that many live performances and recordings, if you notice, if you check the videos, you will find that the microphones are kept this way. So this is another example of stereophonic sound production recording, which is very common. Remember, it is called Bloomline pair. It is named after its inventor. Also, there are certain constraints on the speakers by which you will reproduce the sound. So two speakers should be kept at the corners of the room ideally and separated by some distance, not small, not very large. The overlap area or the best area where stereophonic effect can be understood or rendered can be moved by changing the speaker strength. So making right speaker more powerful or left speaker more powerful, you can shift that area. And if the speakers are placed too close, then it is almost like a monophonic effect. It's not the not the stereophonic. And if they are kept too wide, then they create a hole in the center. So to be careful, if you have to experiment, listen to the sound carefully, and then place the speakers. So for example, here In this room, which is of the shape of a rectangle, two speakers are kept at these corners. The best listening impact comes when a person is sitting at the center in such a way that this angle is 90° to 40°. So people sitting in somewhat in this region will experience the stereophonic production or reproduction. But if you are sitting here or here, then the stereophonic reproduction is lost. Now, if you have room, again a rectangular, but if you are keeping the two speaker widthwise, then you have a large areas in which the stereophonic effect will be lost. In a very small area, the stereophonic effect is obtained. So see to it that your seating arrangement, your seating place is that place. If you keep them in the corner, then this area of best reproduction will shift out. So you have to be careful. Next, we talk about sound diffusers. Sound diffusers, as the name suggests, if the sound hits a hard surface, it is reflected. The reflected sound can mix with the direct sound and may produce interference. It may produce unwanted high frequencies and low frequencies sound, maxima and minima. Sorry. And therefore diffusers are needed. In a room of any decent size, diffusers becomes very important part. As the name suggests, these are some simple diffusers in diagram. This is a triangular one, so sound comes at a high intensity, but you can see on this side the sound is reflected away this way, on this side the sound is reflected in a different way. This is one way to diffuse it. Other way to diffuse is by putting uneven surfaces. So it diffuses less here and diffuses more here. And the third way is to put a spherical surface. So sound coming flat is reflected in different directions. But we have diffusion grating also. Diffusion grating follows the principle of simple diffraction grating. Sound is a wave, so it gets diffracted through narrow apertures. Remember that the dimension of the aperture must be comparable to the wavelength of sound. Just like in light, you have diffraction gratings. The diffraction gratings, single slit diffraction, multiple slit diffraction. When the light passes through the diffraction grating, it diffracts in many ways. So here is one design of diffraction grating. Typically, these will go inside and go outside. These are all the grooves which are made. If you look at the walls of the theater, you will find large number of such grooves made. They all work like a diffraction grating to diffuse the sound so that there are no strong reflections. These depth and width of the grooves must be of the order of the wavelength of the sound used, especially at a lower wavelength. So if you have 100 hertz frequency, perhaps the depth should be around a meter, half a meter or so, and the width should be comparable to the wavelength of high-end frequencies. So well depth and well width are the two parameters. Typically on such a diffraction grating, if a sound falls from one direction, it is diffracted in multiple directions, diffused in multiple directions. Sound absorbers are very important. All porous material absorb high frequencies. Porous materials. So at your home, if you have carpets, if you have curtains, bed sheets, upholstery of any type, where a lot of small holes are there, they absorb a lot of sound. There are acoustic tiles which are available. You can check it online. These tiles are available with multiple small holes in them. Sponge is there. So if you can stick all these in your room, they will absorb a lot of sound. If you are living in an environment which is noisy, then you can perhaps consider doing it. So porous material typically absorb a lot of high frequencies. They get converted into heat, little bit of heat. Hard materials absorb well at low frequencies. So like plaster, wood, tiles, walls, etc. They're all hard materials and they absorb well at low frequencies. And these facts can be used to tune a room. So the purpose for which a room is being built, these facts can be used to tune it, to make it slightly tuned to high frequency or tuned to a lower frequency. So acoustic designers or acoustic engineers do all these very effectively in order to bring out the most of from an auditorium. So for example, you can remove curtains and upholstery, keep the wooden chairs exposed, and the room will get tuned to high frequencies. Put lot of upholstery and absorbers, room will get tuned to low frequencies. So all these can be adjusted. Helmholtz resonator can absorb at selected frequency. If you want certain frequency removed from the reproduction, then you can use Helmholtz resonator. Most of you are familiar with it. You know that it has a characteristic oscillating frequency and that can be absorbed. There are many designs which are available. I recommend you to figure it out and check it. We come to the problem. Not many. Let me just discuss some of them. Few of it you can write the answers. In binaural sound production, why are the two microphones placed in the dummy head rather than merely given the same separation in the air? So can anyone try to answer this? I think I have shown you the binaural production. We can go back, check that for a while. Here it is. So what it's asking is, why do you want to put a dummy head? Remove the dummy head. Just put these two in air. Okay. So why do you want a dummy head? Just put them in air. And it's a very straightforward answer. In fact, many of you should be able to guess it. The answer is very straightforward. In our true listening experience, the sound is conducted through our head also, from left side to right side. Our two ears are not placed in air. So if you want to mimic it suitably, then it's better to keep them on a dummy head so that the sound effect which travels through the head, that also can be taken into consideration. What is the difference between a binaural system and a stereophonic system for recording and reproducing sound? I think that we have discussed that detail, so there is no point in getting into more. Which gives the best listening environment, the dipole surround or matching surround? Dipole surround, as we have discussed. What is dipole surround? So dipole surround is nothing but your dipole surround is stereophonic. If you have two microphones, two speakers, there are two poles of the sound, so it's a dipole surround. While if you have a multi-channel audio, then it's a matching surround. So which is better? So think about it. What will decide what is better? Answer to the question is that yes, Namishka, true. What you are saying is some of the sound energy can be transmitted through the head and some damping can happen. So as I said, the real life can mimic. You can mimic the real life situation. Okay. Now coming to the answer to this one. So what decides what is better? So what decides what is better is the real life. Now in our real life, the sound is surround sound. I mean the real surround sound, multi-channel surround sound. So if I'm talking to you right now, you will find that the signals are coming from the, of course, whatever I'm talking I can hear, but signals are coming from outside the windows, from the roadside, from the other part of the home, etc. etc. So the real life is a multi-channel surround sound, and therefore a multi-channel matching surround is always better compared to the dipole surround. Calculate the frequencies of the first three resonances of a room with the dimensions 5 meter, 10 meter, 2.5 meter. Do they have any significance acoustically? So this is straightforward. We have already seen this formula. So length is 5 meter, width is 5 meter to 10 meter, height is 2.5 meter. So just to simplify the entire calculation, let me find out the linear dimensions. So only length is 5 meters. I'll keep 5. As I said, L, M, N, they are all integers. So this is first 3. So I'll put L as 1. A square and square root will cancel out. This becomes 1 upon 5. 5 into 2 will give you 10. So it's 340 by 10. 340 by 10 would be 340 divided by 10. That will give you 34 hertz. Now, would it be acoustically significant? Answer is yes. So this room will resonate along its length at a frequency of 34 hertz. Now we can hear anywhere about 20 hertz. So this frequency would be acoustically relevant. And then it will go in the multiple. So 34 into 2. So that would give you 68 hertz. Would that be relevant? Yes, it would be relevant. By the time L reaches to 4, you will reach to around 130 hertz, which resonates with the male voice. And by the time L reaches to 8, you will reach to 260 hertz or something, which will resonate with female voice. So these frequencies, along the length, the frequencies will match. Check along the height what frequencies would you get. Would they be significant? Along the other dimension, 10 meter. 10 meter should have been the length, but nevertheless, along the other dimensions, what are your frequencies, and figure it out. Dipole sound question mark, I don't understand. You can ask me post class discussion. Okay, we are almost towards the end. Draw a diagram of a room with the dimensions in a ratio 4:3 and indicate the favorite listening areas of the two different placement of the pair of speakers in a stereo system. I think we have already done it actually. So there's no point in doing it again. Suppose the time amplitude trading ratio is found to be 100 microsecond per dB if one speaker is zero point 0.2. That means if the delay is 100 microsecond, then no. So 1 dB of intensity difference can be compensated with a delay of 100 microsecond. That means if one source is weaker by 1 dB, then you can keep that source closer in such a way that the sound reaches to us 100 microsecond earlier than the other source. Is that question? Is that data? It is. If one speaker is zero point 0.2 meter farther away than a second, how much greater must its sound power level be in order that the sound image will appear to be on the median plane or appear to be in the center? So all you have to figure out that if the speaker is 0 0.2 meter away, then how much would be the delay introduced? That is what you have to calculate. So you know the distance upon time is velocity. Velocity is 340 and distance is 0.2. So 0.2 divided by 340 will give you the delay time. I don't have a calculator handy. You can do that calculation. 0.2 divided by 340, that will give you the delay time, and then you can use this figure to find out how much greater must its sound power level be. So 100 microsecond per dB divided by the delay that you will get here. So let me just quickly find my calculator. Now I'll just put zero point 0.2 divided by 340. That gives me 0.00058. This is the delay 0.00058. Now I can take 100. Yeah, so it gives me, if I use that micro also, so 1, 2, 3, 4, 5, 6, so 0.17 dB. So my answer comes out to be 0.17 dB difference. So if you increase the sound level, so if you push one speaker behind by zero point 0.2 meter, then you have to make it louder by 0.17 dB so that the resultant sound image remains at the center or median plane. We can stop at this point. Thank you.